Yeah, so let me start by talking about what motivates these forces. So over the past 10 years or so, building on previous results, there has been a series of coincidences that were observed in the infrared sector of gravity and gauge theory in asymptotically spacetimes. Gravity. I'm going to call them asymptotically Minkowski spacetimes rather than flat spacetimes, just so you know that we have in the setting in which one usually does, for example, relativity or quantum field theory. So it's about that. And so these coincidences, you may be surprised if I'm using this word, but let me kind of say a few more words about them. So there's a lot that we keep encountering. Some of them are now understood as precise equivalences. Between, and we'll see this in the course, between asymptotic symmetries, soft theorems, and memory effects in various theories, and usually at the leading order. Some of them are not quite understood, so they are still awaiting explanation. And both of these sort of led in the past few years to the proposal that gravity in four-dimensional asymptotically flat spacetimes may be potentially related to some kind of conformal field theory that lives in two lower number of dimensions or one lower number of dimensions, depending on your point of view. So this is to be compared or contrasted to the more or much better established ADS-CRT correspondence. So I would just say that in this realm that there are just, what we will see in this course hints at a deeper connection perhaps between gravity and conformal field theories. I'm not going to discuss that very much in this course. So okay, since you see, maybe these last 2 points are a little bit more controversial, or really like we don't understand them very well, and since this is a course for you, for first-year graduate students, we're going to just focus on the things that you understand pretty well by now. And so, so this is the motivation. So what is this course about? So, as I said, it's going to focus on this first point above. And so, we can summarize these equivalences through the following diagram, which in some earlier sort of works has been referred to as the infrared triangle. I'm going to put it in quotes because there is much more to it, as we understand now, than just this triangle. But for now, let me just roughly speaking say that the triangle is basically illustrates a set of 3 subjects that will live at the corners. So one of them is the subject of solved theorems. The other one is the subject of asymptotic symmetries. Or I'm also going to refer to them sometimes as large gauge symmetries. And the other one, I'm not sure if you can see. Can you see if I write here? The other one is memory effect. Okay, and so there's connections between these three subjects that we will explore in this course. And so the edges, on the edges I'm going to indicate what these connections are. So soft theorems, roughly speaking, so I'm going to introduce, so today is going to be about understanding these. So just hold on for a moment, but let me say a few words about them. They are the results in quantum field theory that are known since the 60s that relate scattering amplitudes with and without low energy massless particles. So about 10 years ago, these were understood. So in quantum field theory, they are understood, like studying, for example, gauge invariance of this amplitude. These amplitudes they lead to results related to conservation of low charges. So we'll discuss this more in these lectures and maybe next lectures. But the idea is that they are actually related more generally to asymptotic symmetries, which we'll also discuss next lecture, through a conservation law, or through a collection of Ward identities. So symmetries in general, via Newton's theorem, give rise to conserved charges. In this case, we'll have a more subtle set of symmetries that are so-called asymptotic or large-scale symmetries. We'll define and explain it next time. And they can nevertheless be associated with some set of charges that are non-trivial, so they have a non-vanishing action on your physical phase space. And then the conservation law associated to those charges turns out to be closely related to the soft theorems encountered in quantum field theory. Now, what's about the relation to these memory effects? So memory effects are again things that were well studied in particular in the context of gravitational waves. So these are observables associated to the low frequency sector of gravitational waves, and they turn out to be related to soft theorems very simply by a Fourier transform. So this edge will be able to understand really well, and it's very basic, the connection here. Whereas, via these two sets of equivalences, we also arrive at some relationship between asymptotic symmetries and memory effects, but this is a little bit more subtle, and I'm not sure how much time we're going to have to talk about that. Now, so the literature on the subject is by now quite vast, so there's a lot of discussions of these things. And I have drawn one triangle. Turns out that, so the best understood soft theorem since Weinberg is the leading soft theorem. That one is a very non-controversial result. It's just a fact, almost a triviality about scattering amplitudes in the low energy limit. So the fact that it's called a theorem maybe is too, makes it sound like fancier than it actually is, and we'll see this in this lecture. So we are just going to focus on these leading soft theorems, but I should say, even if they're very basic, they're actually quite interesting, and they are related to a lot of infrared aspects of scattering amplitudes more generally, and they are really essential, for example, if you're interested in particle collisions in the jets and stuff like that. So they play an instrumental role there. And so we will start from here, because these are the best established sort of things in this context, and in particular we'll just focus on the leading ones, and we'll then try to sort of just move on along these triangles to understand first the connection to asymptotic symmetries, and we're also going to talk about memory effects. We're going to illustrate this triangle in a particular context, namely that of gravity in four-dimensional asymptotically flat spacetimes in the leading sector, where we'll just basically establish this triangle. This is probably going to be in the third lecture. Then in the last lecture, it's still quite open, so depending on how people find these lectures, we might talk about various topics, and I will take some quiz later on about what people would like to hear about. So this is the best understood. So we will start here. And I should reiterate what Damian said, that it's very important that everyone asks questions, so please do let me know if anything is unclear. And hopefully, I'm trying to make these lectures as self-contained as possible, but yeah, if there's anything that's not clear, please do interrupt and ask me. So let's begin. So today I'm just going to talk about basically the low energy radiation. So first of all, what is radiation? So you may have heard in your E&M class the word Raclariu, which in German literally means radiation due to acceleration. And before discussing, so the idea is that this is a classical phenomenon, and you would have learned about this, for example, if you studied electromagnetism, so Jackson, for example. So we're gonna start there, and then we're gonna see that actually the same phenomena can be extracted from some quantum scaling amplitudes, and they lead to some puzzles. So this is sort of where we are going today. So there is the classical. Okay, so let's focus on the classical case first. So let me consider the idealized scenario where we have a particle that moves at some form momentum p in space-time, and that at some moment in time and space experiences a sudden kick. Okay, so it changes. So this is characterized by a change in its form momentum from p to p prime. And so we have a sudden kick at equal to 0 and x equal to 0 without loss of generality. So I should also say that much of what I'm going to discuss today you can read about in chapter 6 of Peskin and Schroeder. Although I may assert this from. So this first bit you can literally follow what's going on by looking at this chapter. Okay, but so you may, first of all, let me just, so we'll analyze this problem in much detail, but let me first say some words about, you may think, okay, this is a very unreasonable situation. Usually when you have some particle, it will interact with other stuff over some finite amount of time and space, and then it will go off to infinity, like with some change. So you may think, okay, that these form momenta are just constant in the large time limits, but you know, in general, we don't have such localized sudden interactions. So in fact, as we'll see later on, it's an exercise. It doesn't matter. For the low energy radiation that we'll be describing and discussing in these lectures, the fact that this interaction is sudden actually doesn't matter that much. So in particular, you can generalize what will be discussed today to a scenario where we have the particle basically moving along some straight line trajectory in the far past and the far future, as long as the interaction is localized and under certain assumption of the frequency of the radiation that we are interested in. So basically the frequency, so the energy of the radiation is smaller than the inverse scaling time. You'll see that the results that we'll be discussing, you will be able to show very explicitly, and I'm going to sketch how that goes. That what we'll be discussing won't really be affected. So, okay, but for now, let's just stick to this ideal case scenario. And let's analyze what's going on. So, in order to understand, So here, of course, another thing that I should say is that this particle experiences some acceleration at this point in time. Yeah? And so we expect the radiation to be emitted, so we are looking for to find this radiation. So of course, you can just solve Maxwell's equations to do that. And the first thing we need is the source, right? So here we have a particle, so that is characterized by current, density. So let's first look at the case where the particle was, if the particle was actually at rest. Then the current density, so at rest at x vector, 3 vector is equal to 0. In this case, the current density will just be given by the charge localized at that point. So we have only a potential component not vanishing. So we have something looking like this. And then we have charge. Sorry, I should say that this particle also carries some charge, some electric charge. Yeah, so this is just the charge. I'm basically just writing down the formula for the charge density of the particle that's localized at x equal to 0. Now, I can trivially just rewrite this as an integral over some time t of the same 4 vector, and then introduce here a 4-dimensional delta function. So basically, I'm just trying to analyze this formula in a more covariant way, such that we generalize it to the case where the particle is actually moving along an arbitrary trajectory. So for now, I'm just rewriting the formula for a charge at rest, where I have to tell you what the trajectory. So in this particular, for a particle at rest, its for location is just given by the time, and x, it's sitting at x equal to 0. So you just have something like this, and in particular, dy by dt is equal to 1, 0. So this is just the for velocity in this case. So we see that this is just, in this formula, this is just dy by dt. And here you can just trivially, for this particular choice of the trajectory, you can just evaluate the integral over time to arrive at the first one. Okay, so there's nothing fancy happening here. Now, what you can check is that actually this formula is invariant under reparameterizations of this time t, and you should have seen this in some E&M courses, the relativistic case. So, and that basically allows us to then write down a formula for a more general trajectory for this particle by just starting with the second line there. So this sort of suggests that for such more general trajectories, we can just, that are parameterized by some function y, that's a function of this time tau. We have an integral over d tau. I'm pulling out the electric charge E, and then I have d y by d tau, and then a delta function, 4-dimensional delta function of x minus y of tau. Yeah, and this formula you would have, again, very standard formula for a particle moving along some wave line. For the current density associated to a particle. Now, one thing that you can do is that you can check this current is actually conserved, as it should be. And I'm not going to do this here, it's an exercise. So, integral over the full space-time of the divergence of this current J integrated against the function with compact support. Is equal to 0. Okay, and now, given that equipped with this formula for the current density, we can go back to our problem and write down the formula for the current density for this particular case. So here we have a particular, all we need to do is to basically write down this trajectory. So y is a function of t. So there, so what is this trajectory? Well, what we know is that if I take d by d tau of the trajectory, I'm going to get, for tau less than 0, I'm going to get some sort of momentum p divided by the mass of the particle, and for tau greater than tau 0, I'm going to get p prime divided by m, okay? So, basically we have the trajectory be given by, and I should have said it, in this case it's momentum, I'm taking them to be constant. There is the only place where we have acceleration is at t equal to 0, tau equal to 0. So, tau less than 0, and p prime mu divided by m, tau for tau greater than 0, okay? So this is pretty straightforward, and yeah, you can take y mu by d tau will give us mu, which you can just literally read off after that to confirm this result. Sorry, I should say that this is constant, except for the tau. Okay, so now I can just take this and plug it into this formula for the current density. I'm not sure if I should write here. Should people see this board? Should I use it or no?
The left half.
Okay, maybe I'll just use it. So substituting, let's call this the gradient star. So into the formula for J mu, we have the following. So J mu x is, and I can just look here. So we can split the integral over tau that in general runs from minus infinity to infinity into an integral from minus infinity to 0 with this current density and integral from 0 to infinity with this other bit. So you have an integral from 0 to infinity of d tau, and then we have p mu divided by, I'm sorry, I should have said, I mean, this m is just the mass of the particle, it's not here. Should be obvious. And then we have delta for x minus p divided by m tau, p prime. This is for, tau greater than 0. And then we have, and I'm also missing the charge E. Okay, just substituting into here. And then we have an integral from minus infinity to 0. Again, we have a factor of E, and then we have d tau p mu divided by m, delta for x minus p divided by m tau. Yeah? This is pretty straightforward. So now, given this current density, we are interested in the electromagnetic field sourced by this particle. And I'm gonna work in the standard Lorentz gauge, where the gauge potential Maxwell's equations can just be written as a differential equation for the gauge potential. So box of A mu is equal to J mu. So Lorentz gauge mu A mu is equal to 0, and Maxwell's equations reduce to just box, where this box is the four-dimensional Laplacian. Mu is A. And now we can, so you should have seen this many times before. You can just solve it by Fourier transform and then Fourier transforming back. So basically what we want to do is now the Fourier transform this equation, plug in the formula for the Fourier transform of J, and then invert that. So this is how you're going to arrive at the formula for the gauge field, and hence also the field strength, which is, so say that the field strength is just dA equals reactive dA. Okay, so I take this with Fourier transform on both sides. We get the Fourier transform of A, and now it's a function of the form momentum K, is minus 1 over K squared J Fourier transform, where I'm going to work in mostly plus signature. Unlike Peskin and Schroeder, who work in the mostly minus signature, so if you want to compare the formulas and write them down to theirs, you have to take that into account. And so, well, here the Fourier transform is defined as in the usual way, so it's just an integral over d for x of e to the minus I k of x, j mu of x. And I'm also using, so for example, k squared is the 4-vector k squared, right? Contracted with the measure, just here. So whenever I don't put any arrows on your vectors, it's going to mean we're going to talk that 4 vectors are involved, whereas when I put arrows in the vector, those are the 3D-dimensional, the spatial components of the vector. Okay, so just, yeah, so now all we have to do is to take our formula for this current density and Fourier transform it. But luckily, you see, it's kind of trivial to do that, because here we have these 4-dimensional delta functions in x, so I can just evaluate this integral over x and absorb those delta functions in the process. So basically what you get, so again we have two pieces, the integral over tau remains, so you have integral from 0 to infinity of d tau, and then we have p prime mu divided by m, but now x in this e to the minus ikx gets replaced by p prime divided by m tau, so you have e minus ik dot p prime divided by m tau. And then we have the other piece, which is integral from minus infinity to 0 of d tau, p mu divided by m, e to the minus ik dot p divided by m tau. So for the second term, all you have to do is to remove the times. Now, you quickly realize that because of the fact that the integrals over tau goes from minus infinity to infinity, And here we just have an exponential of an imaginary bit, right? Because of momenta and everything are real. So these things are not going to converge at the upper and lower limits of integration here. But you can, as we do in quantum field theory, you can regulate this integral by adding a little I epsilon with the corresponding sign. And the signs you want to add here, so you shift this by minus I epsilon, and you shift this by plus I epsilon. So the signs here are different. Here you want this to converge, so basically to vanish as tau goes to infinity. So this means that as tau goes to infinity, this has to fall off to 0 for finite epsilon. So you need minus sign here, and similarly here you want this to vanish for tau goes to minus infinity. So you want the sign here to be a plus I epsilon. And then now we can just evaluate these integrals. It's just the integral over an exponential, so you just get a very simple formula. So we find that J mu in Fourier space is given by minus I epsilon. So all we have is we're bringing down a factor of 1 over k dot p prime divided by m. But the factors of m actually cancel, so you are left with just p prime mu divided by k dot p prime minus I epsilon minus p mu k divided by k dot p plus I epsilon. So this is an important formula, and we're going to see it again later. But for now, let's now use this to find the electromagnetic field profile and the energy radiated through this wave. So this is what we are looking for.
So this is a classical calculation. So is there an intuition for the epsilon prescription in this classical calculation? Aside from inverted.
No, so we are going to come back to this epsilon prescription when we go to the quantum case, and then it's going to be related to whether you have whether you choose to look at retarded or advanced solutions or whatnot. And at this point, you really need these signs to go in this way because otherwise the integrals won't converge. But actually, I'm going to drop. I mean, it's not very important actually for everything else. I'm going to say at least for now. But it's a good question. And by the way, it has to be in this way because this thing has to be real. So you take on the complex conjugate. Yeah. Okay. Okay, so now I want to plug that in to find sorry, I should ask any other questions. Okay, so this should be, hopefully, we're going slowly. What's the time?
It's 11:01.
Thanks very much. Okay, so still not perfect. Yeah, so we plug that in. And we find that, and now, so I can just plug it in and I can automatically also do the Fourier transform back to position space in one step because it's just a very simple formula. So this just is given by d for k divided by 2 pi to the 4 e to the plus I k dot x this time, and then e times I divided by k squared. And apologies, I'm going to now move, it's still under the integral, but I don't have space. And we now just have to plug in for this formula. So p prime mu divided by k dot p prime minus I epsilon minus p mu divided by k dot p plus I epsilon. Yeah, and the Fourier transform, this is just the inverse Fourier transform, and we have a plus sign and a factor of 1 over 2 pi to the 4, because you want to take the Fourier transform twice to get back to the original starting point. Yeah, so now it's not an x, it's times sine. So now you should be familiar with how to evaluate such integrals from, for example, quantum field theory. When you compute, for example, when you go from like the momentum space version of the propagator to the position space version of the propagator, what we usually do is to first do the integral over k0, and then we do the integral over the spatial components. So we're going to do this now as well. So but to do that, it's a bit, well, not very tricky, but we need to be careful of where the poles. We can do that via counter integration, but we have to look at where the poles are here. And we have poles, there's two poles when k squared is equal to 0, and there is one pole when k dot p is equal to I epsilon, and another one when k dot p is equal to minus I epsilon. And so we want to look at the complex k0 plane. And the pole locations, let me write them down explicitly. Are k squared equal to minus k0 squared plus k squared. So this means that we have a pole and k0 is plus minus k plus minus k minus I epsilon. Sorry, this is equal to 0. Okay? Sorry, this is,
Yeah, just
plus minus k. Sorry, for now it's just plus minus k because I don't have an I epsilon in the k squared yet. But I have to put it in to be able to evaluate these integrals. Okay, and then we have another one where k p prime is minus I epsilon, so this means that whatever, you can expand it out. I'm not gonna waste time doing this. So let me just write one. So we have minus k0 p0 prime plus k3 vector dot p prime 3 vector is equal to minus I epsilon, and you can just solve for k0. You have to find the pole. And similarly here. And so we see that the poles are, so let's look at these two. So here we have poles at on opposite sides of the real k0 axis because of the different I epsilon prescriptions. So those, in principle, they would be somewhere along the real axis depending on what k dot k scalar product with p vector would be. But because of the I epsilon prescriptions, they get pushed in different directions of these axes, and in particular, we find that so we have a pole, the k dot p equal to 0 goes up because of the plus I epsilon, and the other one goes down. Oh, I guess we have color, right? So these are the ones associated with these guys. And then here for k squared, whatever it is, however I shift it, I can either give it plus I epsilon or minus I epsilon. We'll see later on that those correspond to recurring or advanced solutions respectively. So let's look, it turns out that the retarded solution corresponds to shifting, to introducing the plus I epsilon here, I believe. And so k0 would be plus minus k minus I epsilon. Okay, I'm just shifting, like shifting this by plus I epsilon. So this means that I have two additional poles somewhere, like they were originally on the axis and they get shifted down. So this is k0 is minus k, and k0 is. Yeah, there's four poles, one of them is above the axis and the other one is below. The other three are below. Now, with this information, we can now evaluate the integral over k0. And we can consider, we should consider actually the two cases, namely the case where t, so here I can split x into t and x3 vectors, so there are two cases to consider, one when t is less than 0 and one when t is greater than 0. So for t less than 0, since e to the I k of x is e to the minus I k0 t plus I k of x, we see that I have to close, when t is negative, at large k0, this goes as e to the I times I, and that's minus something large, so that's the place where I should close it, because I want the contribution from the contract infinity to vanish. So we have something like this. We find that we pick up just this one pole here, when k dot p is equal to 0, and the result is just an integral now over 3 momentum e to the I k dot x 3 vector, and k0 now gets set to basically k dot p divided by p0, so you have minus it k dot p divided by p0, and then you have the 2 pi I from the contour from the residue theorem, and another 2 pi because I split that from the integral over d for k.
Sorry. Didn't you also like the k dot p prime should be in the upper plane and k dot p in the lower plane? Like if you see the equation with your if you divide by
Yes.
minus p prime plus I epsilon over p prime.
No, you are, I think you are right, yeah. So k, this is plus I epsilon. No, because it's minus k0. So k p prime is minus I epsilon. Oh, sorry, k. I did mess something up. So k p prime.
Alright, okay, yeah. It should be k p prime equals plus I epsilon.
Yeah, sorry. Yeah, exactly. Sorry. Thank you. Yeah, okay. And then now it's all fine.
Yeah, no, it's fine.
Thank you for pointing that out. Great. Any other titles? Any other things I'm missing? Okay, but hopefully, because as I said, I was, yeah. Hopefully I got the signs right, but there is some sign changes that you have to do compared to testing. Okay, so but the result in the end of the day, of course, shouldn't depend on the convention, so that's another way to make sure that the answer is correct. Sorry, what?
It would, well, I mean, it would be p prime in that integral.
I haven't finished writing
okay.
that.
Oh, sorry.
Sorry. Yeah. Yeah, so we have p mu, and then we have epsilon divided by p0, and then we have this spread. Yeah, I'm just evaluating the, and it is a p because I'm dosing it in the upper half plane. Yeah. With the observation about my signs of I epsilon, but this picture is correct.
Okay.
Okay, so let's think about what this means. So it turns out that so I can evaluate, so we can look in the rest frame of the particle. In this case, P mu is just P0 and 0. And plugging that up there, we find that a integral of x is integral over k 2 pi cubed e to the I k dot x. So P3 vector is 0, so this factor drops out. I can cancel some factors of 2 pi and some factors of I. And we are left with, E divided by K squared 1 0. Yeah, and you remember that here this K squared is actually evaluated at K0 is equal to whatever the value of the residue is, right? And so the K0 in this formula for this particular choice of P will drop out, so here you end up with the 3 vector K as opposed to the 4 vector. So maybe there is, now that I'm looking at it, it looks like there is also some sign. Let's not worry too much about the overall signs. So this you may just recognize as just the Coulomb potential of a charge of a particle at rest. Okay, so now what about, and if you can take this and boost it, of course. You can use the Lorentz covariance of this formula to obtain what's known as the linear Richard field of a particle moving at constant velocity. Now, what about after? So this was before the scattering. What about after the scattering? So t greater than 0. So here we need to, just by the same logic, we now need to close in the lower half plane. And now we have 3 poles that we pick up. I'm not going to draw it just not over popular diagram, but the point is that one of them is just going to be the corresponding linear Richard solution due to a charge at rest once we go to the rest frame in the final state. So this is going to be analogous to what we find here. So let's ignore that for now, but we have 2 additional contributions that should come from radiation. So let's look at those, because those are what we are interested in. So I'm now gonna, so this subscript here means that I'm throwing away the contribution that would be of this form with P goes to P prime, and I'm focusing on what comes from the poles in K squared. And this is V3K divided by 2 pi cubed, and then E divided by 2 absolute value K, e to the I, K dot x, and then we find P prime mu divided by K dot P prime minus P mu divided by K dot plus the convex conjugate. And it's a little bit of algebra, so all of this evaluated at K0 equal to plus absolute value K. So the convex conjugate comes from so this first line is from one of the poles, the second line is from the other pole. You can just compactly write them as the first contribution plus the convex conjugate, both of which are evaluated at K0 equal to plus absolute value of K. And this can also be written as the real part of the Fourier transform over the spatial momenta. Okay, of something that I'm going to call A mu of K, which is just P divided by K P prime mu K dot P prime minus P mu K. So yeah. So this is something that you should remember because we're going to encounter it later on. But before doing so, let's also, so any questions about what's happening so far? So this is a contribution that comes from basically radiation. And the radiation is generated due to the fact that we have this instantaneous kick at t equal to 0. So to calculate so now we want to look at the energy that's radiated, and then we're gonna see some funny behavior. So what we really need to do is to actually compute the field strength associated to this gauge field configuration. And it turns out to be not that bad. So we have the electric field, so this is given by this F0I, and so it is B0 AI minus BI A0, and we have BI, which is epsilon I JK, JK, using the summation and Einstein summation convention, and so this is just epsilon I JK D J AK times 2, something like that. But I'm using the anti-symmetry under JK to just combine the two terms into one. So in Fourier space, so again, it's quite a bit easier to look at the formulas for these in Fourier space, and so just because basically under Fourier transform, the derivatives will just change into momenta with the corresponding components of the momenta. And so we find that epsilon ik is just minus iki a0 k plus ik0 a. So whenever there's tildes, we have functions of momenta, so we have in Fourier space, and then b tilde ki is I k cross product now because of this epsilon ijk a k 3 vector, the ith component of that, and so this is you can check that this actually using the formula for the electric field. Here, you can show that this is nothing but the unit k vector crossed with the Fourier transform of the electric field, the I component. Okay? And now, the energy radiated away is given by the standard formula. You can write it in a Lorentz covariant form in terms of contractions affecting mu, but in this more standard, like language, more basic language, we can just write it in terms of absolute values, the sum of the absolute value of E and B. So we just have a half d3x absolute value electric field squared plus absolute value magnetic field squared, which is just a half. And you can just, it's a simple exercise to show if you plug in for the Fourier expressions for these guys, that this can also be written as an integral over the momenta of the Fourier transform of the electric field dotted into its complex conjugate. And if you're puzzled that now B disappeared, you shouldn't be, because really B tilde, we just related it to E tilde here, and so these two terms actually combine into just one. So finally, so the problem now just boils down to evaluating this object, and we can do that by introducing polarization tensors. So these are the orthogonality and completeness conditions, and then we may be familiar with this. So epsilon mu is equal to 0, and also sum over lambda, and there's two polarizations for the photons. So I'm not talking about photons yet, but yeah, anyways. So we have epsilon mu symmetrized epsilon lambda a mu complex conjugate symmetrized over mu should be the spacetime metric as a mu. And so I can now, since the zero component of the electric field vanishes, right, by definition, I can just replace this by, I can write this in a more covariant way as epsilon mu, dotted to era mu, and then use this completeness relation for the polarization tensors. So we have this thing is just sum over lambda 1, 2. And we just have absolute value of epsilon lambda k dotted into epsilon k absolute value squared. And I can also rewrite this in terms of my A, because that's the thing we found, and this turns out to be just k squared and sum over lambda 1, 2. Epsilon lambda k. Not sure if people can still see that, but it's covered by the. Okay, we can do that. So a tilde k squared. Yeah, then there's just a factor of k coming from this formula that relates pk to a. Okay, but let's see, do we still have a formula for that? So actually, this AK is just appearing here, so I can just now plug it in. And I'm going to stop after this. It's not too much over time for the first bit, but if we try this, it has been up. Before, and I can plug it in and then plug it back into the formula for the energy. So this is what we're looking after. We have the energy radiated away is given by E squared divided by 2, sum over lambda, and then integral over d3k divided by 2 pi cubed and then we have epsilon lambda k dotted into p prime divided by k dot p minus p divided by k dot p absolute value squared. Okay, and this we're going to talk about this in the next lecture, and sort of like explain what the physics behind it is, and then we're going to rederive, sort of like look at the same problem from a quantum, like sort of scattering amplitude perspective, and we're going to run into some puzzle. So that's what we're going to do. So great, I guess.
Questions first?
Ah, sorry, questions. Yes.
Can you explain one more time how you got to the top line?
Here.
No, yeah, that one.
Here.
Yes.
Yeah, so I'm just rewriting this as epsilon mu k contracted to epsilon mu k, but I can also write this as epsilon mu k epsilon mu k eta mu nu, and I can plug in the formula for eta mu nu from here, and then just rearrange
Oh.
this. Yeah. And use the fact that the electric field is zero.
And you said the first component was 0.
Well, the first component of E0 is like just F0, 0, so that's
Yeah.
zero.
So I don't need to summarize hopefully what we did before. So let's continue with this formula. So we have the absolute value squared of this quantity here. So we can actually now expand it out and use the completeness relation for the polarization tensors again to simplify it. So this is actually just the integral. And I'm going to split this measure also into a sort of a radial piece and an angular piece. So we can write the integral over d3k as k squared dk divided by 2 pi squared. And then we have an integral over some angular bit that doesn't depend on k, doesn't depend on the absolute value of k, but rather just on the angular dependence. So we have this factor of 2, I'm combining it with that. And then we have e squared divided by k squared. Sorry, 1 second. I think. So here you should, I think, have corrected me because I think I missed a factor of 1 over k squared. Oh, no, sorry. It's just that. No, sorry. I was just confused my notes. Yeah, so the idea now is that, so we can now also isolate the, so k is a null vector, so I can isolate the magnitude and trade basically this k for a k hat. And so I can write this as e squared divided by k squared and replace the k's there by hats. So we have, and expand this out, right? So there is like 3 terms. 2 of them are going to involve, after using the completeness relation for epsilon, they're going to involve p prime squared and p squared, and the other ones are going to involve a cross product of p and p prime. Okay? So here again, minus 2p dot p prime divided by k dot p prime with hats on the k's because I just factored out the magnitude. And then we have plus m squared divided by k hat dot p squared plus m squared divided by k hat dot p prime squared. And since now again, so now the magnitudes here cancel, and this bit now doesn't depend on the magnitude of k anymore, but just the angles. Okay, so let's call this part now only depends, yeah, so now let's call this I p and p prime. Now, Let's take a look. So let's take a look at the regimes from in which, like, the behavior of this integral. So one thing that we notice is that the integral is actually, so this integral now goes from 0 to infinity in principle, but since nothing else here depends on k, this integral is going to blow up at high energy. So we have to put a high energy cutoff here. I'm going to replace this by k max. And in fact, we will see that actually this formula in the more general case actually only holds in the limit when k is smaller than some kind of cutoff. Anyways, I'm going to assign it as an exercise in a moment. So it's okay to put that cutoff there. Now, another thing that we notice is that in the ultra relativistic limit, basically what we have there is that this p dot p, so you can turn this problem around and think about p dot p prime as some kind of center of mass energy, some energy squared. If this is much larger than the mass of the particle, we call that an ultra relativistic limit. And in that case, so here we have basically p dot p prime much bigger than m. And so the first term dominates. Another case in which this term dominates is when the alternatively you can just take the particle that is scattering to be massless. In that case, but in that case, you're going to start running into subtleties, because in the case where the particle is massless, you can also generate collinear singularities that come from when k hat dot p and k hat dot p prime approaches 0. This is not possible for massive particles, so for massive p and p prime, but it can be possible if p and p prime were null themselves. So m is 0. Okay, that's not possible otherwise. But nevertheless, even so, in the ultra-relativistic limit, these guys can become actually quite small. And so the dominant contributions to these integrals are going to come from when, sorry, let me just do the easier case where we just have, let's say m is approximately 0. Let's say that p and p prime are approximately null. In that case, the dominant contribution to the integral is going to come from when k dot p is 0, k dot p prime is 0. And in fact, this corresponds to the case where we have radiation basically be approximately of this sort. So we have final state radiation that is collimated as sort of like runs along the same direction as the final particle. And we have initial state radiation that moves along with the initial particle. So here we already encountered this phenomenon of jets that people talk about in particle physics. Oh, sorry, here I'm doing something silly. Like, well, anyway, let me not say where it attaches to. The point is that it's aligned with the initial particle versus the final particle. And this is really the phenomenon of jets. So in particle collisions, when you collide particles at very high energy, they're going to emit radiation, but this radiation is not typically going to be isotropically distributed. It will tend to be basically like aligned with the directions of the particles. So we see this from sort of this already at this classical analysis. And you can now perform these angular integrals here, and I'm not going to do it for you. It's probably easiest to just use Mathematica. But the result is that the energy simplifies, and it's approximately now given in this limit by to a factor by an integral from 0 to k max dk, and then you get a log of q squared divided by m squared, where q squared, I'm defining it to be the difference between p and p prime squared. Particularly, if I take m goes to 0, this thing blows up, and this is the statement of collinear divergences. We don't have an infrared divergence from this limit when k goes to 0 in the energy emitted. However, there is an infrared divergence if one is interested in knowing how many photons, so how many quanta of energy are emitted. So we are just doing, everything we discussed so far is classical, but we can still think about wave packets that are quantized. So they are quanta of energy what notation did I use? K, yeah, HK. And so we can now count how many quanta there are in this stuff that is emitted. So the number of photons is just an integral over the differential energy divided by basically h bar k. Yeah. So all I need, I just need to take this formula and divide by k, and here we are going to get integral from so c squared divided by 2 pi squared, and then we have times, okay, in general, there is this other bit, so this I p prime that we discussed before. It's log of whatever in this approximation. It's log of k squared divided by q squared divided by m, but I'm just going to keep it more generally. The point is that now we see that there is another divergence that pops up, which comes from the limit when k goes to 0. So we get a logarithmic divergence from low energy photons. So can replace this by some cutoff. Okay, so we have an infinite number of photons that are emitted in this process. Now, that's all fine. So before we move on to discussing, so since we started talking about photons, now you may imagine that we can obtain the same results by studying the scattering amplitudes. And more recently, there's been a lot of developments in the field of basically like classical limits, so extracting classical observables from scattering amplitudes. And what we're going to see now in the rest of this lecture is that the simplest example of that phenomenon. So we're going to write down some scattering amplitude, we're going to perform some classical limit, and we're going to see that we're going to recover this classically computed result. So you can imagine, and that's going to be the most basic example of this more general, I guess, program. And we're going to discuss, so this divergence here is going to be very closely related to the problem of infrared divergences in quantum field theory. So we're also going to touch on that right now. But before doing that, there is a little exercise that I advertised at the beginning. So I said, so we considered this idealized case where we had just a kick. But I also mentioned that actually the spectrum of this radiation is not affected by allowing for this interaction to not just be localized, but rather extending it. So I want you to show that the formula for A and the energy and so on still holds, so long, so to leading order in an expansion where K, or the energy of this photon, is much smaller than the scattering time, than the inverse of the scattering time. So you can think about this. So how would you do this? Let me also give a hint. So this particular case, now I can write it like I did before. So I can approximate. I would start by writing some current that now is basically what we had before. So P mu tau divided by M for tau less than T. So in this region, all the way in the back, it's still moving along a constant trajectory. In the far future, it's still moving along a constant trajectory. But then there's going to be some stuff that we don't know. It can be very complicated in the in interval where tau belongs to minus t. Yeah. And then now the idea is to show that whatever this contribution is, it will be subleading in an expansion in this limit. So you will use the stationary phase approximation to show that the contribution from here okay. And intuitively, this actually, you can think about this intuitively. So what does it mean to have a low frequency mode? Well, it means that it's or low energy mode, it means you have a very long wavelength mode. So as long as the wavelength of that mode is much bigger than the extent over which the interaction happens, you shouldn't expect the radiation profile to be sensitive to the interaction, and hence you would expect the radiation pattern to be universal, and hence given by the same formula that we had in this ideal case where we just had the sudden kick. So yeah, this is the one. Yes, this 1 over t is my k max. Yes. Essentially, although there's going to be different cutoffs that we're going to discuss in a moment, but yeah. Okay, so we already learned some important lessons from here. So let me just not write them down, but let me state them while I erase the board. So the lessons are that there is a universal radiation pattern that is generated in some simple processes, such as a particle interacting with some other stuff and scattering. We saw that the number of photons. So if you assume the existence of a quantum of energy, the number of photons diverges in the limit when the energy of the quanta goes to 0. So it turns out that you can see these features also by looking at scattering amplitudes. So there is a quantum computation, so calculation, which you can do, which allows you to extract similar phenomena and more, right? If you're interested in, like, for example, quantum corrections and stuff like that, of course, you would want to start here in quantum field theory and then take some limits to get the classical result, but then you can also derive some other interesting phenomena. So this is why it's important to move away from this classical approximation. I mean, this is just the motivation, standard motivation of why we do quantum field theory. So let me just remind you what the scattering amplitude is. So, and apologies if this is super well known to everyone. So we have some time evolution, we have some scattering, where we have some number of particles at some initial time that are in some state. Let me use some quantum mechanics analogy. Of course, we want these particles to live in some Fock space and be freely moving at some very early times. But for now, let's assume that we can put them all in some state that I'm going to denote by psi initial. Then we have, they will interact, and we assume, so the usual assumption in quantum field theory is that they interact over some finite amount of time. So this is similar to what we saw here in this classical problem, as well as some finite extent in space. So interactions are localized. This is the assumption that every quantum field theory textbook starts with. So it's localized in space and time. And so at very early times and at very late times, particles are approximately freely moving. Now you can see, it's again, the analogy to what we discussed before starts to become hopefully clear. So, okay, they interact. The interaction is going to be characterized by the S matrix. So, it's given by a unitary operator, just like for closed systems in quantum mechanics. And we're going to call this S, the S matrix. And hence, at some late time, T final, we end up with some state that is related to the initial state by this operator. Sorry. Fine. So we have this is S psi initial. So again, I just want to emphasize all you have to do is to prepare some initial state, and then this S matrix, if you were to know what the whole theory was, then you would have access to this operator, and it would just act with it and determine the state at any later time. But what we usually want to do in quantum mechanics is to figure out what is the probability to find the final state in some given other state. Okay? So let's call this psi out, which generically is going to be different from the psi fin. This thing is going to be given by just the absolute value squared of the inner product of the psi out with this psi fin, right? So this goes under the name of an exclusive cross-section, and it is defined to be the absolute value squared of psi out inner product with psi fin, which is also via this equation. I can also write it as psi out S psi in. So this you may have seen, it's a familiar formula for the scattering amplitude. Its absolute value squared is just the cross section. So this thing in here is called the scattering amplitude. Yeah, so exclusive. So let's give an example. So whatever, we start off with some initial momentum eigenstates, for example, of some charged particles, and they interact maybe electromagnetically, and then they evolve into some final state. And I may be interested in knowing what is the probability that the final state contains, I don't know, 1 photon, 2 photons, or 100 photons. Okay, so this is what this thing would be computing. You could compute that using this formula. But sometimes you're not only interested in exclusive cross-sections, you may be interested in inclusive cross-sections. So you may be interested, instead of the question, what's the probability that I find my system in some given state, I could be interested in what's the probability in finding my system in one of these different states. So for example, what's the probability that I find my system in a state with 1, 2, 3, or 10 photons, so up to 10 photons. So this is an inclusive cross-section. And here you would be summing over some out states that you care about. And just, yeah, and I would take the sum over those out states of the absolute value of this formula that we had before for the inclusive cross-section. In. Yeah, so let me just be clear, sum over a subset of possible configurations that we care about. And of course, just to emphasize the fact that so the unitary, like knowing whether we have unitary S matrix in an arbitrary quantum field theory is a very hard problem because, as you know, there's divergences, both UV and IR, and moreover, the S matrix is typically not known for like simple theories. We usually compute it in perturbation theory. It's very hard to check that this I mean, the way we define it, we expect it to be a unitary operator. And the reason why we want it to be unitary is because we wanted the sum over all probabilities. If we look at what's the probability in finding the final particle to be in one of any possible final state, that should be 1. And so let me just write that down. So summing over all out states should give 1. And indeed, if you sum over all out of psi out s psi in absolute value squared, I can also write this as psi in s dagger psi out s psi in sum over all out, and all possible out states should give us a complete basis, and so this should just become the identity insertion. So there should be psi in s dagger s psi in, and so if the S matrix is a unitary operator, this should be 1. Okay, so this is why, of course, we'd expect the S matrix to be unitary, and our initial states are normal. I mean, yeah, normalized to 1. Okay, but yeah, so we don't have access, unfortunately, in quantum field theory to the full S matrix, and so we do the best that we can. People do the best they can usually and compute scattering amplitudes, and they computed them in perturbation theory in some small parameter. So first of all, amplitudes are the building blocks for these observables, so for these cross sections, and they are computed in perturbation theory usually. So for example, in QED, you would have the coupling between the photons and matter, the electric charge would be small. Yeah, so just you can think about this as the interaction strength. Okay, so let's do an example. So I thought it's not going to matter what particle content. So one of the punchlines is going to be that it shouldn't, and this was shown by Weinberg a long time ago, If we are interested in the radiation produced by some scattering process, its low frequency components doesn't depend on the type of the particles that we are considering. So it doesn't depend whether they are like, fermions or scalars or like whatnot. The form of this radiation at low energies is universal. So because it's simpler, ideally we would want, and in fact you can read in Peskin and Schroeder about QED and how to do the calculation in QED, but it's actually, it's easier to just forget about the fact that, in QED we have fermions and just talk about scalar QED. Yeah, I decided to do this, and then I realized that maybe it's just as hard, so or just as easy. So it really doesn't matter, but you should just get the idea, and then you can go home and do the exercise in QED if you'd like. So what's scalar QED? So basically, I just don't want to worry about the fact that, in QED we have fermions. So here we just have scalars, complex scalars, and there is some Lagrangian. There is a kinetic term for the scalars. And then there is some mass term for the scalars, and then now there is some interactions. So there is a phi to the 4 interaction, and there is some coupling to electromagnetism in this way. So this is the kinetic term for electromagnetism. This is the interaction among scalars. And this big D here is the gauge covariant derivative, which tells you that the scalars also interact with the electromagnetic field. So I can split this Lagrangian into a free piece and an interacting piece, like in quantum field theory. So the free piece is just going to contain quadratic terms. It's basically the kinetic terms, and the interaction term is going to contain cubic and higher. And let me write it down explicitly just to expand now, because it's going to then be easier. So basically where we are going with this is that we want to look at all diagrams that involve the emission of a photon. And so we need to know the Feynman rules. So let's write down the interaction bit. So this is, so now I'm expanding out this term. There is going to be a term that involves a phi dagger phi, and there's going to be a term that involves a phi dagger phi, right? So those are the two terms that appear, so I'm just going to write them on 2 different lines. So we have this one that's linear in A. And then there is this one, and then there is the interaction among scalars. I'm just going to copy that over. So, okay, there's 3 kinds of vertices. Now, we are only interested in, as I said, radiation that is emitted. Or the emission of photons. So this means that when I look at when we write down the Feynman diagrams, this one won't matter very much, right? Because this just couples the scalar to itself. So there we don't have, we're only interested, we want to isolate the bits of this where we have the photon attaching to the matter particle. So the relevant vertices are the following. So we have one where we just have a photon emitted from matter from one of these scalars. So let's say we have an initial momentum k, and we have a final momentum k prime. And then from this, so you can do it carefully by going to Fourier space and whatnot to find out the Feynman rules. But roughly speaking, we see here what this vertex would add, would contribute. Basically, because of the derivatives here, we get factors of k and k prime associated with the scalars, the incoming and outgoing scalars. So what you find is that the vertex associated to this diagram is basically IE k plus k prime mu. So sorry, this photon also has a dangling index mu, right? That would be associated with that. And so this is from the first term. Now from the second term, we can also have something that looks like this. So again, we have an incoming scalar, an outgoing scalar, and then we have two photons be emitted from the same point. So here we have, okay, and we can put in momenta, but actually it doesn't matter. From this diagram, you can just read off that the vertex here just has to be minus 2i e squared eta mu nu. Right, there is no derivatives on the phi's, and I can just write a mu is a mu nu, a mu a nu, eta mu nu, and then there is a factor of 2 from the symmetry of this photons under exchange. So these are the vertices. Sorry, and I should also say there's also going to be something like this. But won't care about. For what we are, for this radiative pattern. So the propagators, so again, I should emphasize that you should just feel free to interrupt me anytime and ask any questions. So yeah. Yeah, so we'll be interested in a radiation that's emitted in a scattering process. So you can already see that from this diagram like this is exactly what we classically analyzed before, right? We had diagram where we had basically like a particle that changed momentum and emitted some radiation. So the quantized version of that is, of course, that really should correspond to this, and then this diagram, and then arbitrary many emissions, but this is the simplest order 0 calculation that we can do, where we have a matter particle emitting one photon. So the propagators are as follows. So minus I. So for the photon, we just have the standard minus I eta mu nu divided by k squared minus I epsilon. And for the scalar, we just have minus I divided by k squared plus m squared minus I epsilon. And this is just the Feynman prescription. And we also have polarizations. for incoming and outgoing photons. And basically, this gives us all the Feynman rules that we need to compute the diagrams involving the emission of a photon. So there's several classes of diagrams that we can consider. So the simplest ones are these ones, where the photon, so we have an arbitrary number of scalar particles, and then the photon is emitted from some, so let me call the photon momentum Q. Sorry, I think the K is like the P here, and Q is the momentum of the photon that is emitted. Sorry, I just realized that I'm mixing, this is K, this is, sorry, I'm gonna call this Q just for clarity. Apologies about this. It's P squared, and then this is gonna be Q. Yeah, so now I think more or less consistent. Those K's there should be P, but okay, hopefully it's not too confusing. So we have this one where the photon attaches to an external line. We have one where 2 photons get emitted like this from the outer vertex. And then we have another class of diagrams where the photon attaches to some internal line that can be either a loop or it can just be an internal propagator. So these are the only possibilities for one photon emission. And the point is that we can just calculate them very explicitly. So let's look at the first one. So the first one, using the Feynman rules, can be written like this: an plus 1 q, and then we have some momenta p1 to pn. And also here we should keep in mind that there is some dependence on the helicity. The photon that can be emitted with a positive or with a negative helicity. So this, from the Feynman rules, I just can look at the diagram there, and we have some vertex. So the internal propagator here is just pi plus q. So using this formula here, you can show that the vertex is basically IE, and then we have pi plus q plus pi mu divided by pi plus q squared plus mi squared minus I epsilon, and this is dotted to the polarization tensor epsilon lambda mu of q. And then, so this gives us, it's like stripping off this vertex, and now we are left with an amplitude with all of the other external momenta unchanged, except for now we have a leg that has some off-shell momentum that will be basically like pi plus q. So we have some an with momenta p1 to pn, some off-shell momentum pi plus q, and it should be clear that while all of the pi's and the q are on shell, because this is on shell scattering amplitude, and the LSE prescription basically puts those on shell. Now what we get here is something that it's off shell, right? Because we have one of the external legs would now be basically this pi plus q, and that's not an on shell momenta because pi dot q doesn't have to vanish. So this was a note here that there is an off-shell bit, but actually in the limit, we are really, let's consider the limit in which the energy of this photon that's emitted is much smaller than the center of mass energy, for example, sorry, there is no center of mass energy here, but much smaller than all of the other momenta, let's say. So, sorry, so in particular in that limit, so notice that pi plus q squared is pi squared plus q squared plus 2pi dot q. So the difference between a case where this was on shell and off shell is basically order q. So in the limit as q goes to 0, which is also called a soft limit, this guy here can be ignored, and you can analyze the behavior of this factor. And what you find is that so now you can use the orthogonality of the polarization onto the q, and also the on-shell condition on pi and q squared to rewrite this as 2ie, and then pi dot epsilon lambda q divided by 2 pi dot q minus I epsilon times an, where now this an is an honest on-shell amplitude that depends on on-shell momenta p1 to pn. And then the key thing here, sorry, I should have said, is that notice that in the limit when q goes to 0, this factor blows up. So now it's reasonable to have thrown away the contributions from this an here that were order q. Order q, because in particular, when doing this expansion, I have already ignored terms that are order 1 in a small q limit. So yeah, you can think about this as just the Taylor or Laurent expansion, because there is a pole in q. The key thing, and sorry, I just noticed, Damian, that we are basically done, but I think we also started later. I didn't account for that. I'm not sure how much I'm allowed to go. I think I'm just going to skip. Okay, perfect. That's perfect. Yeah, because then I can just say the punchline. Well, one of the points is that, first of all, this looks very similar to what we've seen before, right? Right? It's like one of these factors that we've seen in the previous calculation. First of all, this goes to infinity as q goes to 0. So this is the fact number 1. Now there is a collection of other facts. This, unfortunately, so I was planning to do it in like glory detail. I thought I would have time, but the fact number 2 is that, and now it's left as an exercise, apologies, is that diagrams of the form, so this was 1, this is 2, and this is 3. So these ones give no pole as q goes to 0, and hence are subleading. In the soft limit. Now, roughly speaking, the reason for that is that here, if I take one of the QIs to go to 0, this interim propagator does not get put on shell. This means that there is no pole generated. This means that in a limit, when you take Q1 to 0, then this thing is going to be order 1. And similarly here, you can split this into 2 contributions. One of them where you have basically a loop. So you have an integral over this loop momenta, but there is another case where this just attaches to an internal line where you don't have a loop, so you don't have to integrate. But again, in both of these cases, as you take Q to 0, this internal line is not going to go on shell. And you can show that, and hence there's not going to be any contribution that blows up in the limit when you take Q to 0. So that's roughly speaking why this is. And then the fact 3 is that all of this is related to what we had before. So we only care about this formula. So to relate to a previous computation, we just observe that basically the process that we looked at before had an incoming line of momentum p, an outgoing line of momentum p prime, and some other stuff that we don't care about. And then we had basically, so in this case, we can have the photon, an outgoing photon. We looked at the retarded solution, so we can have an outgoing photon either attaching to the incoming line, or we can have an outgoing photon attached to the outgoing line. So these are the diagrams contributing to classical computation before. Yeah, so we have to take the sum of these two, and we can just use in the small q limit, we basically have two contributions that look like what we just computed here. So what we find is that this, sorry, now I'm just gonna compute this. I'm gonna go here. Just in pictures, so this is just gonna be equal to IE, so as q goes to 0, this is just IE p prime dot epsilon lambda q divided by p prime dot q minus p dot epsilon lambda q divided by p dot q times the amplitude where we don't have this photon anymore. Okay? So this is no photon. And so you now recognize that this is exactly the Bremsstrahlung factor that we had before. And you can now compute a probability. Sorry, this is the last thing very quickly, just to leave you with something, with a puzzle. If we compute a probability to emit one photon with energy less than some Q max, this is given by the cross section that we had before. So we have to take an integral over the phase space measure. So integral over d3q 2 pi cubed. Then we have a 1 over 2q0 from 0 to some k max. And then we have sum over lambda and some e squared. And then we have absolute value of, sorry, this e squared comes from here. We just have to take the absolute value of this prefactor here. That's the probability to get a photon be emitted, to emit a photon. Okay? But this you may recognize from the formulas from what we've written before. So here we have a probability, but this is actually infinity. So it's integral from 0 to k max. And you can again pull out some, like write the integral as an integral of the magnitude of q, or really like involving q0, and then things will cancel and you get dq divided by q. And then you have some I of p prime, which is the same angular distribution that we defined before. And this diverges, okay? Because this integral here ranges from 0 to some k max. There is some logarithmic. So previously we found, this is basically the same answer that we found before for the number of photons emitted. But here it popped up, so the same answer popped up is the probability of emitting one zero energy photon. And that's a bit ridiculous because probabilities should not be infinite. You can think about it, and next time, basically, we are gonna sort of like dig a bit more into this puzzle, and we're gonna see that the only way in which this can make sense is if actually this other bit goes to zero, okay? And we are gonna understand why this goes to zero and why that's related to asymptotic, basically asymptotic symmetries, large gauge symmetries in this context. And well, that's basically where we are going. So this is the infrared. It's a version of the infrared problem in QED. Thank you.